This talk is going to describe a design for improving interpreters that are compiled to WebAssembly using meta tracing. And we gave this talk already at Popple last month. This will be a replica of that talk, but hopefully clearer than last time. And you know, one important thing as we're talking about trying to build a bunch of distinct tools, and we're interested to see if any of these tools will be useful elsewhere outside of, the design we're talking about here. So let me start from the following scenario. Developers will write programs in high-level interpreted languages. I have Ruby, JavaScript here. And then the interpreters for these languages are compiled down to WebAssembly. And then many users invoke these programs many times. And each invocation, though it may be on dynamic user input represented by these numbers here, the program itself and the interpreter are static. And the WebAssembly hosts, like those for function as a service or distributed compute systems, they will execute these invocations. And the problem that we're trying to solve is that interpreting these programs is slow. So ideally, we solve this without modifying the interpreter in any way. And note that this scenario hints that maybe perhaps our solution could be offline. So between these repeated invocations in the WebAssembly engine. We'll argue that the problem that we're attempting to solve is important because it's already been attempted elsewhere. So for example, one approach that has been taken is to build a just-in-time compiler for the interpreter in question. And this is, the traditional method. This would look like finding hot functions that an interpreter executes, compiling that program's bytecode down to WebAssembly, and then patching the WebAssembly module or patching this new WebAssembly into the running instance somehow. And Dimitri from Igalia demonstrated this approach last year at Wasm.io. And it's a natural, common sense approach, makes sense, but not all interpreters have a JIT. And the WebAssembly spec has no standard way to kind of patch up these instances with JIT compiled functions. And this approach is too risky for some of the hosts in our scenario. They don't want to add to the running code at runtime. In fact, the risk of these subtle JIT bugs at runtime motivated recent partial evaluation work by Chris and Max. And so in our scenario, what this would look like is that this tool combines an interpreter and program bytecode, both statically known, to derive an interpreter that is specialized to a program. And Chris and Max built Weevil to do just this for interpreters compiled to WebAssembly. And they have a paper that explains the idea. And this, in general, is a well-studied approach that's taken by Graal and Truffle, but it is complex. It does require some minimal source code changes, and it's naturally limited to the information that is statically available. And our approach is different. So our approach is based on trace-based optimization, and specifically meta tracing is a subtopic that's aimed at improving the performance of these interpreters. So what happens in the scenario is we collect traces of WebAssembly programs. Using those traces, we create optimized fragments for hot regions of code, and then we insert these optimized fragments into new optimized programs. And we'll describe all this later in future slides. The reason for choosing this approach, or the reasons, include that no JIT is needed. And so we don't need to build a new JIT for each interpreter. And many kinds of interpreters can benefit. We hope also that using our approach, we can build these distinct reusable tools for each phase, and they might be useful elsewhere. And we also believe that but because we can do offline transformations, we can improve on previous systems that had to be online. We don't have to make up the runtime overhead that online systems had to. And the primary question here is, can we improve interpreter speed using this approach? And so let me just say here that there is a history of trace-based infrastructure, and I'll just briefly note that ours differs in that we expect our approach to apply to more languages than other systems and to work offline. All right, let me jump into an example to kind of explain what meta tracing is. So here we're interpreting Java bytecode. So you have a Java program on the left that's compiled to Java bytecode on the right. And why are we using Java? Well, we have a research prototype that does this, right? So we have a Java interpreter, but of course one can and should compile Java directly to WebAssembly. It's beside the point here. So our Java program has a loop, and we'll call this the user loop. So the body of this user loop compiles to the Java bytecode on the right. And we also have a Java interpreter written in C that's compiled to the WebAssembly on the right. And this also has a loop. And we'll call this the dispatch loop. So this loop retrieves the bytecode for a given program counter and executes the bytecode implementation. So two loops, the user loop and the dispatch loop. And we'll observe that most execution time is spent or is due to that user loop on top. And when interpreting the Java bytecode using this interpreter, much of the dispatch loop execution is overhead. So how does meta tracing improve this? Well, let's focus in on three operations within the user loop. The load, the add, and the store, and I've kind of split out this interpreter, which was C compiled to WebAssembly, and I've split it out as a simplified control flow graph. The red instructions are the WebAssembly instructions involved in the dispatch loop, and the green brackets represent the bytecode implementations. And they're not, all the WebAssembly code is not shown here for brevity. So if we trace the execution of these operations, we can detect a pattern. So we'll see that we do some dispatch logic, then we actually run the bytecode, and then we do some more dispatch logic, and we do that again, and we do that again. So what meta tracing does is it detects this pattern, the hot loop, and it will emit an optimized fragment of the user loop, hopefully minus the dispatch overhead. So an intuition here is that once these user loop instructions are laid out in straight line code, an optimizer has many more opportunities for optimization. But of course, I kind of have an asterisk here for these guards, right? What about operations inside a loop that, for example, exit the loop? What do we do about control flow that exits this optimized fragment? So let's talk about off-trace exits. So let's focus in on the comparison instruction in our loop up at the top, compare greater than or equals to. You can see the interpreter logic for that opcode, and you can see how we would trace this part of the code. We'd have the branch table for the dispatch, dispatching to this bytecode, and then we'd have a branch if that we'd record the decision taken to either exit the loop or not. All right, so this branch table corresponds to the switch statement in the bytecode, and we believe that meta tracing can predict this for a hot loop. We know which is the next bytecode we're going to execute, but the branch if corresponds to user logic based on data, input data, and this is the condition that may end the loop. And these tests must remain in the optimized fragment in some form. And the form we're going to call that is guards. And this test, this branch if, may be inverted, or maybe it may become more specific, but the guard must remain. And so if the guard fails during execution of the optimized fragment, we have an off-trace exit. So we're leaving the assumed path of the hot loop, and the meta tracing system must de-optimize to the original interpreter. So typically in other systems, this involves resetting the interpreter state and executing a go-to to the right location in the interpreter. This is a known problem for metatracing. It's a solved problem, but it's especially a problem for us in WebAssembly because the structured control flow paradigm prevents us from doing this go-to. So we don't have an ability to go to in WebAssembly. All right. So I've given you kind of a rough idea of what metatracing is. Let me talk about how our system will attempt to implement metatracing for interpreters compiled to WebAssembly. After I describe this, I'll talk in more detail about how to find loops, several of these blocks. So finding loops and de-optimization. Each block here represents a separate tool that may or may not be useful elsewhere. And the green check marks means that we have some kind of working prototype. So how does this work? First, we will take a WebAssembly program plus interpreter and use one or more runs to collect a trace. Then offline, we'll use the trace to specialize this interpreter to the program. So ideally, we'd use an existing optimization tool like Wasm Opt. Eventually, we get to the point where we can patch up the WebAssembly interpreter with this specialization, this optimized fragment, and then future invocations will use the optimized version of the interpreter, exiting versus using some mechanism that we'll describe later. So the primary data structure that we're using in the system is the trace. And it's a list of events that can recreate the execution of a WebAssembly program. Let me specify that these are events, control flow events, not, for example, system call events. You can see sort of some of the ones that we're tracing right now. A trace can be saved to a file, though there are limitations to, large executions could be very large files. So how we're doing it today is a naive approach where we insert WebAssembly host calls and capture the decisions made. But we know this will slow things down. There's mitigations I won't talk about, like reducing the number of events, using special hardware. The primary goal for these traces is to help us do meta tracing, but there may be other uses for this, such as building up macro ops that would avoid this off trace exit problem, and for annotating programs with branch hints, which I have something that already does that. So let me dive into more details. Let's talk about how we find the user loops. So we have a trace here on the left. And what we'll do is we'll apply a string algorithm to find tandem repeats. This algorithm comes from DNA sequencing, and it'll find repeated subsequences within a trace. So once we get these repeated substrings, these tandem repeats, do we truly have a user loop, though? Because if we look at the values deciding that branch table instruction, so 29, 27, 162, these are actually byte codes. These may be a part of a loop, but they may just be byte codes. They don't truly identify the user loop. So two observations. In bytecode interpreters, the user loops are identified by the PC, not just by this branch table value. And so we need to know this PC to know when to jump into an optimized fragment when we're getting into a user loop situation that we have an optimized fragment for. And so the key here is to correlate this PC variable to an event, right? We have the branch table instruction down there below, but the PC is actually sitting in this local. And there's two options. We could just use annotations. So all the other systems that I've talked about in a couple slides ago, they have some way of annotating how to figure out the PC, and that's a valid approach. But I actually don't hope to do that. The other approach would be to find these PC candidates automatically, but there's more research needed there. Not going to discuss that too much in this talk. Either option here is acceptable for determining what the PC is. So let me talk about another topic that we're going to dive a little bit deeper into. So how to implement these off-trace exits. If we're executing an optimized trace and we need to leave it, de-optimize the original program, here's some options. We could use on-stack replacement, or we could use something that we call block lifting. So this is an idea that came about from talking with Nick Fitzgerald. Let me talk first about on-stack replacement. So recall that if a guard fails, we need to de-optimize from this optimized fragment back to the original interpreter. So traditionally, VMs do this via on-stack replacement. What does this mean? We fix up the stack used on one side to match what is expected on the other side of a jump. So we regenerate some values and we regenerate some call frames. In our scenario, we need an engine that has two features: restore operation that we can call from the optimized side, and a restore point on the de-optimized side to mark the places that we need to restore to. So for example, let me try to illustrate this with some stacks. So we're executing an optimized fragment. And the stack looks as follows. We were in the main interpreter function, and we had the value 29 in our value stack, but now we're in the optimized fragment at location 31. But what happens is that we've reached an off-trace exit. We've determined, oh, we don't have more optimized code to execute here. We need to de-optimize. But we need to de-optimize to this call stack. We need to look like this to continue execution. So in the de-optimized stack, we're still in the interpreter main function, but we're at a different location. We're at location 75, and the slot that was 29 before needs to have the value 162, for example. So we need different values for our value stack. And also, we may need new frames. So we may need to generate call frames for add and unbox and give them values in order to continue execution at unbox at location 9. So OSR needs to kind of bridge this gap. So how do we do this? The idea with OSR would be that we have a special engine feature that when we generate all the values we need on the left-hand side in the optimized stack, so we generate the 162 and all these other values, we then call restore in some way, and the engine magically recreates the call and value stacks on the right-hand side. It gets us from the left to the right-hand side. So that's how we're thinking about possibly implementing OSR. But there's another option, which is this block lifting approach. So if we get into an optimized fragment, we need to off-trace exit from it. We could use this block lifting. But this is an invasive WebAssembly to WebAssembly transformation. The other was a special engine feature, but here what we'd be doing is we'd be transforming the WebAssembly interpreter itself, right? Or the interpreter that's compiled to WebAssembly, we're gonna like alter it. So the first thing we're going to do is we'd start from this control flow graph and extract or lift each basic block into a function. So let's look at the pseudocode down at the bottom. This is the pseudocode for the kind of the dispatch loop. And instead of having the implementations for each of these switch branches, we've split them out into new functions: iLoad, iAdd, iCompare. So we'd connect all these lifted blocks using tail calls. And these tail calls would allow us to kind of jump from block to block. So that's what I've represented here with return call. And at the end of the iAdd implementation would return call back to the head of the dispatch function. And so then when we need to de-optimize, we insert a tail call to the de-optimized lifted block from the original interpreter inside our de-optimization routine here. So if you see, if the guard isn't true, then we'll return call to the expected location that we were supposed to be in the original the original interpreter. So with this approach, it's unclear how this transformation would alter performance, right? It drastically changes the program. Semantically, it doesn't though, but performance-wise, it may impact the program. And it's unclear still how we deal with all kinds of control flow here, like exceptions, or like if we have other tail calls existing in the in the code. So more research is needed here as well. Okay, so finally, let me summarize by discussing some of the research questions that we're trying to explore here. So the big one is, can this approach improve interpreter speeds? And how does it compare with existing approaches? We talked about traditional JIT compilation and Weevil via partial evaluation. One big question for me is, can we avoid altering the interpreter source code? Do we need to, ask interpreter authors to add annotations or not? Can we do it automatically? We want to know if these tools are useful separately, and maybe there's other applications for them. And of course, we'll be evaluating some of these implementation decisions that I described. So this system is offline. Other systems have been online. Is that a benefit? Some of these techniques that I discussed for loop finding, the tandem repeat finding, or for off trace exits, this OSR versus block lifting, those are some of the questions we're trying to answer with that. And with that, that's the end of my presentation. Thank you very much.
Field questions from the room.
One sec. If anyone was driving a gray Volvo, their lights are on in the garage. So just letting folks know. Great. Thanks.
I can field questions from the room. We have about 10 minutes.
Hi, Andrew. Thanks. I'm wondering, for the on-stack replacement part, you talked about how you could do it with return calls, which is nice. Have you thought about how you could do it with core stack switching?
Yeah, we talked a little bit with Sam at Popple, and we've thought about it in the past. We don't have we don't have all that figured out. In fact, we were thinking about using stack switching almost like as an administrative safe zone in which to set things up before we switch. But yeah, I'd be interested to hear more ideas, because yeah, there might be something there.
Cool. Thanks.
Looks like Ben has his hand raised.
Similar kind of question. So could you also think about using the tail call to transfer to a different version of the frame, which is effectively an unrolled version of the side exit?
Yeah,
So when
there could be more levels there, I think, yeah.
So I've been thinking about this for a while. Basically a side exit it's like an OSR where you have to do loop peeling. And you could generate a version of the bytecode that has all the loops peeled.
Right.
And then takes the state. And so your optimized function basically will tail call into the unoptimized side exit function.
Yeah. That's exactly right. I think we are thinking of all loops need to become this form so that we can restart execution at the head of any loop.
Right. Cool. Thanks.